is it secure? And this is a question that I had for the weekend, and I said, I'll tell you on Wednesday. So here you go. Classical security. So as I already said at the beginning, this is based on an isogeny problem. So given two elliptic curves, can you compute an isogeny between them? So why is this hard? If you have, so Alice's secret is of this degree, so these are the L's from our isogeny graphs. So if L1 to the E1, that means she's done E1 steps around the isogeny graph, the L1 isogeny graph. She knows the path, oops, she knows the path, so she can just do only isogeny computations of degree L1 up to Ln. And that turns out to be this kind of complexity, which David already covered. But an attacker has to compute one isogeny of the really big degree, because he doesn't, Eve, right? Eve doesn't know how to decompose it. And another way of thinking this that's maybe more intuitive, in the graph, in this sort of tire thing, right, the composition of cycles, Alice has to compute one path, and the attacker has to compute naively every path between 2 points, and that's obviously a lot more. Okay, so that's the classical security, and the best variants turn out to be something a bit cleverer, but meet in the middle, it's not that much cleverer, which is O of the square root, the 4th root of P. Okay, quantum security. So I mentioned Kuperberg and Regev already, and there's something called the hidden shift algorithm, which has sub-exponential complexity. So Kuperberg's algorithm requires a sub-exponential number of queries, a sub-exponential number of operations, and a sub-exponential number of qubits. A variant by Regev, he showed how to use a polynomial number of qubits at the expense of some time. And Kuperberg later figured out some more details on that. Not details, but he gave some more trade-offs. And Charles Jan Sukharev applied this attack to CRS, which also applies to C-side because it's the same construction. So what you need to know for the next slide is that part of this attack basically computes lots of paths in the isogeny graph in superposition. I mean, it's way more complicated than that, but the fact that you have to compute paths in superposition means that you need to compute isogenies on a quantum computer, and that's hard. Okay, it's good? Okay, I got a thumbs up, great. So the quantum security depends on what sort of trade-off you take with Regev and Kuperberg, and on quantum evaluation of isogenies. And Dan talked about this yesterday at the ramp session, because most of the previous analysis, although there's been some more precise analysis in the last months, focused on asymptotics, but our new paper from 2 weeks ago, or 1 week ago or something, recently anyway, gives a full computer-verified simulation of quantum evaluation of isogenies for this the smallest NIST security level 1 C-side group action, and we show that it's that long number of nonlinear bit operations. And that tells us that actually the fastest, taking the absolute fastest variant of Kuperberg, so remember that was a sub-exponential number of qubits, and that turns out to be billions. The total cost of the attack is about 2 to the 81 qubit operations, as Dan mentioned yesterday already. So that gives us at least some confidence in the quantum security, as far as we can be confident about these things. And these are our parameters. So you see there's a lot more numbers for CSIDH 12, and that's because it's much easier to do simulations there, because it's smaller. So we have public key size of 64 bytes, private key size of 32 bytes. It takes 85 milliseconds for a full key exchange. And the stack memory is also pretty low, 4,368 bytes. Classical security is 128 bits. And then, well, this is maybe a little bit more conjectural. These high levels, because it's quite hard to do simulations there. But this is roughly the power parameters. Okay, so what can you do? I told you that there's already a constant time implementation. But you can see our new paper, and also a paper by Meyer and Rafe, which will be presented at IndoCrypt, which is not really about constant time implementation, but it's about a fast implementation, and they give some ideas for constant time. So we need a fast constant time implementation. Once we've got that, I added this because there are lots of nice talks on hardware implementation here. So that would be pretty awesome. We have a hardware implementation. More applications. As I said, it's a pretty flexible scheme, so that should be totally possible. And I hope next time I can add your paper to this list. And thank you very much.
So do you have any question or comment?
Hi. This is again related to the SIDH, so maybe I should have asked you before.
That's fine.
But I was looking to see the answer now, so that's why I waited. If I remember well, in SIDH there was this sort of asymmetry from the computational values involved, because one was doing computation over F2 while the other was doing computation over F3. So I wonder if this is still present here, or...
Okay, so I guess what you mean is that Alice starts with 2 isogenies and Bob starts with 3 isogenies, or the other way around, and then they switch. And I suppose in that sense we kind of have the asymmetry, although then it's a bit more subtle because where they have 2 and 3, we've got isogenies of degree 3 up to 400 and something. No, what's the smallest, the second largest one? 387, and then 5 something else. 587? There's lots and lots. Anyway, there's 74 different primes, I know that, rather than 2. And the choice of how many of each one and in which directions is actually the secret key. So that's going to be different. So that asymmetry in that sense is still there. Yeah.
Is there any issue if you're not picking? Is there any issue that it's not a sort of random ideal for the class group, but it's specifically one that's a product of these small ideals of small norms?
So you mean security issue, I guess?
Yeah.
Well, based on our analysis, no, but it's also, I mean, you wouldn't be able to compute it if it was a random ideal, because it would have some huge norm, potentially.
I guess I'm asking, like, is there any data on how these are distributed across the class group? Are there, like, class
How old is there data on that?
Well, there's small examples that we basically tried and
right, I mean, you're not going to compute this huge class group.
right. So the class group is indeed too large at the moment. It seems to complete the structure. With, for instance, small experiments with similarly constructed primes, it looks random. So there's actually one relation exercise item that you can quite easily find, but the others are just random. And we have in our paper actually an argument that's kind of based on heuristics, but there's an argument that if you take, well, basically just a big enough number of these small products, smooth products, it seems likely that it actually covers the whole class group. So we don't have any proof, but there's no reason to think that it's somehow very non-random.
Sorry, so it's time to move to the next talk. So please discuss later if you have any comments or questions.